So yeah, my talk today is bare metal DevOps. Who am I? I moved here to Chicago, it'll be 3 years next week. 3 years ago, moved over from the UK. I work for a local trading company called DIW. Yes, we are hiring. I suppose everyone is used to that. So you can come and talk to us outside at any stage, ask any more questions. I'll probably be at the speakers clinic at some stage today as well. But yeah, bare metal DevOps. Initially, my working title was going to be heavy metal DevOps, but I got a lot of feedback that, you know, a lot of people don't think that heavy metal's cool anymore. And also, Metallica, at least when I was a teenager, was my favorite metal band. But I think the wheels fell off with them when they sued Revlon, because Revlon released a lipstick color called Metallica. And it just went downhill from there. So instead of talking about that heavy metal, I'm going to be talking about this heavy metal. This is a photo of one of the aisles that's full of machines that I look after. From quite the early days of kind of DevOps, when it actually got a name, I started to get a bit frustrated by how the assumption, whenever people were talking about tools and techniques and how that you need to work, the underlying assumption is you're creating a web service that is running on the cloud somewhere, and that DevOps only applies to you if you've got those constraints. For me, this is infrastructure I look after. We've got no internet-facing web services, which actually makes things a lot easier from a general security point of view. Don't use AWS anymore. We'll get into that a bit later. And yet, even with this infrastructure, I cannot do what I do without applying what I like to think of as the way of DevOps. So the core principles that I'm just going to outline briefly apply wherever you're doing DevOps. But I'll be focusing primarily on how these principles are different within your infrastructure, because I believe that the people who are doing the web apps out on the cloud are probably the minority of people who actually need DevOps culture, DevOps practices to make their lives better, to make their jobs more enjoyable, and to deliver more value to the businesses that they work in. So to me, core principles are agile infrastructure, being able to change your infrastructure around you as you're working along, treating your machines as cattle, automation, communication. So starting with the agile infrastructure, you must use configuration management, whether you're using machines out in the cloud, whether you're using containers, whatever you're using, I think you still need to have some type of configuration management. It doesn't care, I don't care, it doesn't matter what flavor of configuration management you're using, as long as it fits in your head and you can manage your systems appropriately. The whole thing being that when you bring up a new machine or a new type of machine, or you reprovision a machine to be doing a specific task, you need to be very confident that when that machine comes up and is ready in production, that it'll be exactly how you expect it to be without any human intervention needed. You need to be able to test and rebuild and repurpose hardware as well. When you're dealing with your own hardware, you can't just terminate a running instance and then forget about it. You've got this hardware that's actually taking up space, potentially consuming power, and is sitting in an accounting book somewhere, slowly depreciating. But you still need to use these principles of testing and rebuilding regularly to ensure that you don't have any bit rot within your machine images, within your configuration, within how your systems expect to run. And ultimately, it's about getting feedback on your systems and about getting deployments completed faster. And the next trick in this is to still use your machines as cattle. Treat them as disposable entities that can go up and down, that can fail, that you can still not worry if they disappear. Again, in my specific environment, we're not using containers. Containers still don't have the network performance that we need. So we don't have any CoreOS or SmartOS or OpenStack or anything like that, but the principle still applies. You need to be able to treat your machines as cattle. So part of this, though, is when you're not running in containers, when you're running on bare metal, is how do you start managing your operating system images? How do you handle going between either upgrading or downgrading between releases of the operating system? In our case, we primarily use Ubuntu. At the moment, we still have some 12.04 machines. We have some 14.04 machines. We've been testing a little bit with 16.04, but we're not quite there yet, primarily because of the great evil that is systemd. And so we still think of the operating system image management that we do is very similar to how, within a cloud context, you'd be managing your operating system images, your machine images. It's very similar, but how we bootstrap the system changes a little bit. So within our boot process, all our machines will PXE boot. So straight away, they'll come up, they'll PXE boot initially. But a plain PXE boot doesn't provide, the only information it really provides to the DHCP server when it initially comes up is its MAC address. And especially when you've got different types of networks, different types of interfaces, and network cards do fail, and you have to swap them out, that's no longer a reliable identifier of this specific machine is this MAC address. So the very first thing we do is we actually simply chain load into iPXE. iPXE is a lovely piece of open source out there which allows you to do a lot of scripting and a lot of automation around how you PXE up a system. And so what we actually do is our very first iPXE script that gets chain loaded actually has a look at the DMI table on the machine. And the other thing that it pulls out and sends to us is the actual serial number of the machine, because that, although not 100% guaranteed, is a lot more stable than a MAC address. And so what happens is it then uses an HTTP call to a web service with the serial number saying, all right, this is the serial number of the machine that I'm on. What configuration do I need? That, again, returns a separate iPXE script, which then gets chain loaded again. But that specifies the VLAN that the machine needs to come up on, specifies the operating system distribution, specifies the specific kernel version that we need to run. And so that then allows the system to be chain loaded and come straight up. We then rely on the Debian live boot packages to actually also pull down the actual root file system as a squashfs. And so by having the kernel and the root file system decoupled, it allows us to test new kernels. There's still a surprising amount of bugs in various kernels at the moment. We've had bugs primarily around network cards and around file systems with some of the abuse that we put the bits and pieces in. Now you'll notice right now we're not doing any disk configuration yet, but yeah, we still have file system bugs, and we'll get to those a bit later. But the Debian live boot system then loads a squashfs, a squash file system, over HTTP, and that is our actual root file system. So it's kept in memory, and our root file system is just read out of RAM very quickly, and that's our base machine. And then after that, it then checks out some configuration scripts from Git, which will actually then set the host name, set up the DHCP client and the operating system, and configure the network interfaces. So there are some classes of machines that we'll possibly do network bonding on. Some of them will be running with 1 gig interfaces. Some of them will be running with 10 gig interfaces. Sometimes we'll chop and change in between them. And ultimately, we rely on a set of scripts to based on the machine configuration, and based on this information that comes back from the HTTP config service, configure up the machine, wire it up, and actually the very last step then is to run the chef client to actually configure the machine as we need it. And that chef client service will then, if we are using the local disks in the machine at the time, it'll configure the machine disks as it needs to be, mount that file system wherever underneath the file system tree we need it to be. And so that way we're kind of managing our machines as disposable, replaceable entities. If we get a new class of hardware, if we need to expand them, we just order more of the same type of machine, give them the same template to run and just up they come. Part of that Chef client, we still have, we've been running on the system for over 4 years now, and part of that is also configuring the RAID controllers in our older machines. We don't use many RAID controllers these days. Most of our system, when we do need some kind of RAID, we'll be using software RAID, because the processors these days are so ridiculously fast that software RAID is so cheap and easy. But some of our older, bigger machines, we still have a mix of RAID controllers, and so we've got a Chef lightweight resource provider that'll actually, given a bit of JSON metadata, configure up the RAID controller as we need it. This is probably the only step that requires some human intervention, is if you change a machine from one class to another. We're a bit paranoid about the state on disk. So if the RAID controller configuration is the same and the file system's got the same label, we'll just mount up the file system. But if it isn't, we'll just stop and say, hey, there may be valuable data on here. I'm not going to blow it away. Just need a human intervention to go and just remove the file system, remove the RAID configuration, run the Chef client again, everything is reconfigured as we need. And so that way we still keep our stuff quick and easy, which brings us into the automation side of things, bringing in new hardware into our fleet. So it's, we run quite a few different hardware classes right now. Most of them actually run with pretty much an identical configuration. So we'll have hardware from different vendors, still running with the same boot script, still running with the same Chef configuration, but they're just brought up initially, and the only difference may be the type of processor, the number of processors, the amount of RAM. And then, as far as configuring the machine and bringing it up, that isn't really important to the configuration management. But the hard parts come around firmware upgrades and diagnostics. So as far as the firmware upgrades, especially running Ubuntu on some of the commercial platforms that we have to spend a bit of time up front. And it's even worse with network card firmware upgrades. We've discovered network firmware bugs as well in some of our controllers. So there's some brands of network card that we'll never touch again, purely because the quality of the firmware in their cards is so poor. And there actually seems to be a correlation between the harder it is to apply a firmware upgrade to a network card, probably the more likely is that it's a terrible quality firmware that's going to be in there in the first place. And also collecting diagnostics. These machines sometimes are still quite expensive. We do have support contracts on them. So being able to automatically send hardware diagnostic information into your monitoring system to tell you, that a failure has happened, how severe the failure is, but also get enough data back that you can get back to the vendors to help them acknowledge that there's a problem, which is sometimes hard, and then actually ship out the replacements and get it all replaced. The other side is around communication. Communication now is no longer with your cloud, only with your cloud provider. Communication now covers things like our data center teams, our network teams, security, especially as we're getting bigger, security becomes more of a problem, something people care more about. And also purchasing and vendor management. There is a terrible habit with the kind of tier one vendors, as they like to call themselves. They all run in different cycles. So what will happen is that they will release a really, really good piece of hardware that a lot of people like, and they will use that to try and get into people that aren't buying the hardware from them. And often there'll be a feature in there that we like, a feature that we need, and we'll go and we'll use that software. Well, we'll buy that platform from the vendor. And then what it'll do is they'll basically decide, all right, well, we've hooked you as a client, you're going to buy from us forevermore, we're not going to invest in the next generations of the hardware. And so what happens is kind of their quality drops down, and they get really surprised when we stop buying hardware from them because their quality is going down. So we try, when we find people within the vendors on the technical side who kind of understand us and the way we work, we try and keep a relationship going in communication with them as to these are the features that are important, these are the problems that we're having, so that hopefully that they maintain it. And so some of the vendors are starting to get a little bit better about maintaining that relationship with us in managing the quality of their hardware, and some of them just don't get the message, and constantly we're getting a kind of carousel of different hardware representatives on the vendor side trying to sell us hardware without actually understanding our business and how we work and what some of the problems are that we face. There are also some additional considerations that you need to think about when you're dealing with your own hardware that don't really apply. Often you'll find the symptoms when it comes to seeing these problems, but there'll be very little, if anything, that you can actually do about it. And these things are mechanical sympathy, networking, monitoring, and forecasting. As far as mechanical sympathy goes, you really need to understand some of the mechanics about what is going on underneath your infrastructure, especially when you're trying to get as much performance as you can. Generally, to me, one of the primary reasons we still run our own infrastructure, besides cost, every time there's a platform refresh, we compare our costs against what the cloud providers have out there, and we're consistently about a third cheaper for our workloads compared to what the providers have at the time. But behind that is actually being able to understand what's going on there. A good example, early on while we were building our infrastructure was purely around disks. We deal with a reasonable amount of data. I wouldn't call us big data. I mean, we've only got a petabyte or two of data that we're dealing with. But there's a lot of it that's still on spinning disks. And so there was one of our developers who started as a young intern with us. He was trying to move data from where we ingest it, convert it, and then pull it out. This was primarily around staging data and growing it out. And he was frustrated at how slow it was streaming data across. We weren't saturating our 10 gig network at the time. And the bottleneck was the disks. And it took him a while to understand that, especially with spinning disks, the more writes that you try and write in parallel to a spinning disk file system, the more seeks you're going to introduce, the slower your latency is going to get, the slower your disk throughput is going to get, because your heads are now seeking all the time to kind of keep up with the different write streams rather than maintain a single write stream on a file system if you can. That way there's a lot less jitter on the heads, and things get better that way. There's also another analogy when it comes to stacking up virtual machines, which Sam Newman uses. He's running the microservices track. But his is specifically around, this applies to containers, but he was speaking about virtual machines at the time. We were working together at a client when I was at ThoughtWorks with him, who was trying to it was a website, they needed to scale their web traffic. And so they had a bunch of VMware clusters at the time that were running their web application servers, and they decided, well, our website response is getting a bit slow, we're not handling enough clients, what we need to do is we need to provision more virtual machines on exactly the same hardware to be able to cope with this load. And Sam was like, well, that's the same as saying, well, I've got the sock drawer, I need to get more socks into this drawer, so the way I'm going to get more socks into this drawer is I'm going to put dividers into the drawer to take up more space to help me wedge in more socks into this drawer. It doesn't work that way. And unfortunately, we get the same approach when it comes to threading. Often, especially junior developers who haven't had much experience yet, they'll think, well, if I've got one thread doing something, especially when it comes to moving data around, if I'm doing one thread, then I'm just going to, and I'm running it on a 12-core machine, then I can just spin up 12 threads, and obviously it'll go 12 times faster. But no, there was a job just recently was actually doing some data validation where it was spinning up 12 threads to do something. A single pass through a day took 4.5 minutes, cutting it from 12 threads to 1 minute. The exact same job finished in 3 minutes. So you can get some quite big gains in performance and throughput by just stopping and stepping back and thinking about what's happening underneath within your infrastructure to do this. Maintaining high availability in these kind of conditions can sometimes be hard as well, because when people are spreading out their load, often they won't think about the thundering herd problem, or about how load will shift if you have a failure with some of your cattle underneath the load. The next piece to worry about is networking. And it's not just a matter of having an IP address to connect to. It's not just a matter of how do I get my data from A to B. We're on our third network topology for just our research infrastructure that I look after. Because as we grow, as we scale, as we get more machines and different types of workloads starting to run within our environment, the way the data flows within our infrastructure changes. And so we need to be able to keep an eye on how that data is flowing and where the bottlenecks are, and try and predict where our next bottleneck is going to be so that we can scale up appropriately. Which then comes to cabling. We've got a fair bit of 40 gig networking within our infrastructure as well. And the original 40 gig networking optics, basically just for a single SFP module right now, they go for about $1,500 just for a single small optical module. So if you're going to run 40 gig fiber between 2 points, you're spending $3,000 on optics for each side on each switch, and then less than $100 for a cable. But if you've got these switches pretty much within a cab, within 10 meters of each other, for less than $100 you can get a direct attach cable, which will do exactly the same thing. So your topologies and your cabling are no longer just about kind of how the machines are interconnecting between each other, but also you need to start to think about physically in space, how you're going to space these things around to optimize your costs and your expenditure on the different types of things. And this also covers protocols. What types of protocols are you going to be running within your network? What kind of protocols are you going to be using between your network and other networks, and how you scale the networks up. Other problems that we run into with cabling specifically are, again, this comes back to problems with old firmware and old network cards, is thinking about cleaning fiber. Fiber relies on light, and if you get bits of dust or bits of dirt stuck in the end of either the optics or on the fibers, being able to keep them clean within your infrastructure is important. Often you'll have connection downgrades or connections drop from a fiber point of view if there's issues tampering with the light limit, but also things with kinks. And kinks in the cable, because light's actually refracting internally within a fiber optic cable. Kinks also have an adverse impact on copper cables, on your twisted pair cables, because often if you kink a cable too much, one side of a link may try and downgrade the speed of the connection, and if your other side of the network card isn't getting that message correctly, you can then get speed mismatches, and you can get all sorts of other problems. And so managing the physical side of things, you need good people on your side to understand the importance of managing these cables and keeping things clean and tidy, but also when you see strange behavior within your environment, being able to identify what's causing that in the first place is actually really important. The next thing that changes when you're running with your own infrastructure is your approach to monitoring. Because monitoring is no longer about, is the instance up? Is my application running? Am I getting the throughput that I expect from my application? But it also comes down to your hardware itself. ECC memory checks are something that we've noticed seems to have some seasonal variability. Kind of the move from winter into spring generally causes a spike within ECC error rates. And so around April, we had probably about a 6-week period here where we were pretty much every day we see at least one ECC error alert. And it was just single alert. And so I was keeping track of the solar weather. It's like, no, the sun was pretty quiet back then. The only thing that we can think is, maybe it's got got to, especially here in Chicago, the winters can be very dry with the cold, and so as spring comes along, humidity changes. Could this be something to do with different types of charged particles floating through the data center, bits and pieces like that. So being able to tell the difference between this is just seasonal variability or, oh, I've actually got a component that's failing, you need historical data to be able to trend and track and to figure out what's going on when it comes to that. Same thing happens, not quite as badly with hard drives. So SMART is the way that you monitor usage kind of general health information from hard drives, both spinners and SSDs. And so, you learn to pick up the different tells from the different hard drives. So one of the areas that you'll start seeing from within a hard drive when you've got either a failing drive controller or a bad cable is your drive itself will start seeing ECC errors from the data that's being written to it as a UDMA transfer from the controller. And so by keeping track of those, if you see a spike in those, generally it means you've got a capacitor that's failing within one of your disk controllers. And so we've had a couple of those, but you also get sometimes it could be issues on the drive itself where it's not actually data related. But we've only really seen this with some of our SSDs where an SSD may not be able to internally maintain the power level to maintain the writes that we're busy hitting it with. And so what will happen is that the power will actually brown out on the SSD system board itself. And so one of the other smart attributes is about unexpected system resets. And so the SSD will then start reporting, hey, I've just rebooted myself. I don't know why, but this was an unexpected reboot within the drive itself. And so by tracking those things, you can start then tracking the status of your disks. Fans are important. Environmental monitoring is important as well. We don't only manage our own data centers. We also have, because we're a trading company, we have machines that are out in shared co-location services and facilities, which are managed by third parties. And sadly, not all data center managers are created equal. So we've had issues where out on the East Coast, we actually had an issue where a certain data center outside of trading hours, so while trading was going on, air conditioning would be running perfectly, but once trading was done, they assumed that heat dissipation wouldn't be a problem. So what they were doing to save on power costs was they were actually shutting down the aircon within the data center during overnight hours. And the thing is, during a hot summer night, the machines are still consuming some power, and so we'd actually see temperature spikes. And so we'd see kind of during the trading hours, things were cool, but then things would heat up overnight, and after a few enough cycles of this, you start to see fan problems, you start to see other problems. And it was ultimately through us providing graphs of us monitoring our environmental temperatures back to the vendors that we were actually able to say, look, we can see you're doing this dodgy stuff. We can see the problems that you're creating, either kind of refund us or fix the problems that you're in. And so it's important to understand kind of the impacts that these environmental conditions have. But again, it's the monitoring, having the data in place around not only your applications and your systems, but also the environments that your systems are running that will allow you to keep a better track of what's going on in your systems. Because big power fluctuations, not only do they shorten the life cycle of components, but probably about about 15 years ago, I'm really starting to feel old. About 15 years ago, there was an issue where I was maintaining a lot of Sun hardware, and we actually had an air conditioner fail within a data center in a warehouse. I was working in retail at the time. And we were running with big Sun 6500 systems, so they CPU blades that mount sideways. And so what had happened, it had gotten so hot within the data center that the heat sinks that Sun had glued on top of the processors had actually fallen off and dropped down, and that actually shorted out, the system board next to them. And so heat can not only cause, small bits of component damage, that can actually take out a whole system by the wheels literally falling off. The next thing that's kind of different when you're running your own hardware is forecasting, being able to understand how your infrastructure is growing around what your needs are going to be, what your requirements are going to be. Because when you're running out in the cloud, you can just spin up new instances and away you go. And retiring machines when you're done with them is pretty simple. But for us, we got things like purchasing lead time. For example, we ordered a new batch of storage for one particular system. We put the order in April. We still don't have the systems yet. They were supposed to ship last week, actually. But we'd ordered a batch of specific type of Seagate drive within them. And Seagate last week announced that they're actually cutting back production on this. And so further up within our supply chain, our forecasters have been expected, while Seagate's going to be churning out so many thousand of these drives a month, all of a sudden Seagate, unexpectedly said, we're just cutting back production of these because we're losing too much money on them. And so now, we're having to switch drive suppliers. We're trying to have to, that has a lot of knock-on effect versus our capacity of needing these systems versus them actually being available. Hard drives are a very good topic. A couple of years ago, there were floods in Taiwan, which not only delayed things quite quickly, but it took many, many months for production to ramp up back to the levels where they were, where people could actually get the hard drives that they needed again. And so this kind of supply chain disruption, you don't know when it's going to go. And so as far as capacity goes, the rule for me is always make sure that you're never running at 100% capacity, because you always need to be able to grow with your bursts and your spikes to be able to do it, but also to be able to run safe experiments. When we're trying new types of hardware, new configurations, or if there's a new type of research that we're doing that may or may not last the 3 years that we depreciate our hardware over, being able to at least repurpose the hardware that you have, you should always be thinking about that when it comes to your purchasing decisions. Amazon Web Services. So, within our infrastructure, we actually started building the research infrastructure that I look after out on Amazon. We started, this was in the early days of VPCs from Amazon, and we started keeping all our data in S3. All our research was done on EC2 instances. We'd spin them up when we need them. We'd shut them down when we didn't need them anymore. And that worked really well for a good number of months. And we got a lot of research done, and it paid for itself. But as we already have to have the data center staff in-house, we already have to have the networking staff in-house for our primary trading activities. Running the numbers on how our research was growing, initially we had researchers who were just trying out new models, trying out new ways of researching, new ways of looking at the data. Once we had a constant stream of, this is research that we need to run every night to help us trade tomorrow, that reached the stage where we were constantly having research running 24/7. And at that stage, the Amazon model kind of breaks down. It's really built for when you need bursty availability. So at that stage, the costs around Amazon started to get quite bad. Even now, whenever we do new hardware refresh, especially for compute, we compare the cost of buying that hardware ourselves versus what the same cost over 3 years at our typical usage load will be on Amazon, and we're still about a third cheaper but running it in-house than actually running our type of load on Amazon is. And so we're constantly keeping an eye on what the costs are out there, because if it does flip, some of these problems go away, and so we should still be able to keep an eye on what's available out there. But there were still a lot of problems, at least in the early days, when we had our own circuits into Amazon. Because of the amount of data that we were using, we actually had leased circuits into Amazon. And the biggest problem that we had there was primarily with S3. As Amazon was adding new capacity into S3, they would actually roll out new IP address blocks to new storage clusters. And so maintaining those IP address block changes within our internal routing tables actually became quite an onerous process, because Amazon wouldn't simply republish them through the BGP peering on the link. They would actually send us an email every week saying, well, these ranges are now available across these links and these ones are not. And so if we didn't upgrade our routing table in sync with Amazon, what would happen is, if we were either pushing up a whole new bunch of data up to Amazon, what would happen is everyone in the office would start complaining, because that would actually end up routing out over our office internet connection and blowing out our internet, trying to get data up into S3 for our research. So ultimately, we spent a good while actually, sizing up how we wanted to store the data internally, rolling that out, and then peeling all our data back from S3 before we actually disconnected our Amazon relationship there. But every now and again, as Amazon rolls out new services, as our needs change, we'll spend time looking at what's out there, just to make sure that what we are doing is still cost effective, and the right solution for what we have. So often I've in the past, when I've spoken about DevOps, I've reiterated the importance of asking questions about not getting stuck in a rut of, I'm doing it this way now, so this is the correct way to do it for all time. That is never the right mindset to be in. You should always be exploring, why are we doing the things that we are doing? What are other people doing to solve similar problems? And are there better ways that I can change what I do to get better value for the organization that I work for, but also to make my life easier and more fulfilling, to focus on different problems and new interesting problems. Gotchas, I've spoken about some of these before. Variable quality of hardware being the top of the list. There's also the quantum state of old machines. There is, and this is tightly coupled with the perception from some parts of the business that depreciated hardware is free. It's with old machines especially, they may be up and running, and you could actually run them through a number of reboot cycles and they'll be fine, and so you can upgrade and downgrade your kernel, you can give them different workloads. But we're nearing the end of actually moving our research infrastructure from one data center to another, primarily around kind of size and cost and cooling considerations. As compute resources become denser these days, where we had the infrastructure just wasn't able to provide us the density of cooling that we needed. But what we had machines that had been powered on and running for over a year to 18 months, and we'd rebooted them a couple of times, but after we'd powered them down and moved them, you plug them back in and they just refused to come up. And so, to me, they're depreciated hardware. So again, as you're treating them as cattle, it's like, well, you've had your free lunch, this one is dead, send it to the knacker's yard and move on to the next one. But depreciated hardware is not free, because when you rely on the old hardware like that, when it dies underneath you, you've got to then think about your forecasting, your supply chain. People are relying on that capacity, perhaps, and so you need to make sure that when that hardware dies, you can replace it. And there's also the human cost of actually maintaining that hardware, diagnosing the hardware, diagnosing the problems, and flipping them over. Again, the platform and the vendor changes. Make sure that when you're building your infrastructure, when you're making sure you're building those blocks that you use to get your machines into the state that you expect, that you're not tightly coupling yourself to any specific technology or vendor tool. Make sure that you can always pull them out. And ideally, especially when you're running within a system, Chef, Puppet, all the rest, make it very easy to inspect the type of machine that you're in right now, the type of system that you're in, and then just say, well, I'm running on this brand of machine, I'm using an LSI RAID controller right now, I need to run the LSI tools to configure it. And so to me, this wraps up what DevOps is not. to me, DevOps is not only about deploying to the cloud, or to containers, or to VMs. There is value in all of those things, but you need to make sure that the value you get out of them is valuable to you compared to the effort that it takes to build and maintain infrastructure around those things. It is definitely not only limited to websites or web services, although we do have websites and web services internally that we present to our internal clients. None of it is public-facing. And very importantly, it's not just another name for your sysadmins, your network admins, your DB admins. And one of the other things that, especially when it comes to people defining what DevOps is, there's a mailing list that Jez set up a while ago. That there's a bunch of us who've been doing DevOps for a long time. Every now and again, an argument will flare up of like, we need to define DevOps because there's many snake oil salesmen out there trying to sell you the DevOps and to say DevOps is this. And so probably the only rule of thumb is, so I'm going to say DevOps is not these things because I currently feel that if someone comes to you and says DevOps is this, they're trying to sell you something and you need to run away because we're still trying to define, I'm still trying to define to myself internally what DevOps is. And to me, a lot of this can roll into the whole no-ops kind of philosophy that's coming up there, where even when you're running out within a cloud infrastructure, you need at least one person within your team who is developing software to understand the mechanical sympathy aspects of where you're running, how you provision these things, how you monitor them, how you maintain them, and how you clean them up at the end. Because with us, when we're buying hardware, that hardware has to be paid for, it has to be accounted for. A similar thing happens up on the cloud where people will spin up instances and just leave them running for ages and forget about them. Someone still has to pay that cloud provider bill at the end of every month. And so you need to ensure that you're getting the value out of these things at the end. Thank you. Any questions?
If you have questions, please put them into the app. First question is also please vote if you haven't voted, and please provide comments to Chris if you haven't. We have 7 minutes for questions. Number one, what kind of security considerations do you have between the machine and your config service, SquashFS, and so forth?
So anyone can get hold of the SquashFS because it is basically a bare machine image. So we actually use Debian Bootstrap to create that initial SquashFS in a directory and then bundle it up. It's very much a minimal with a few extra packages added onto it. So there's nothing sensitive within there. Going up the stack, our Chef clients, we use the Chef has built-in security model for managing the APIs and the bits and pieces. We use encrypted data bags as well. So there is a piece where we use the encrypted data bags for certain bits of information, but also things like the root password within the SquashFS is fairly well known, but very early on, pretty much probably the first thing we do in a Chef client run is we set the root password. But then again, that's just exactly the same hash that's sitting in etc shadow. We've got the same hash that we just, as there's a plain text, go in so you can see the hash, but good luck cracking a bcrypt2 hash. Moving up the stack, when it actually comes to logging onto the machines, some users have access to the machines to actually submit their jobs, to diagnose their jobs, to get their data. What we do as part of the Chef groups and the roles and the environments that we have, we actually define, all our machines are linked into our corporate Active Directory infrastructure. And so we define, well, these groups of machines are being paid for by this business unit, so only people within these groups are allowed to log into the machines. And again, we use SSH to manage all that. We do keep track of kind of local kernel vulnerability exploits, so we have rolling reboots going on within our infrastructure to upgrade the kernels, to upgrade, there was the glibc stuff earlier this year, to kind of maintain those. So we've got that. But ultimately, the value of attacking these systems internally is pretty low, because it'll only be members within a specific group who've got access to those machines anyway. So thankfully, we don't have as many people trying to get into our infrastructure as well, but we do keep track of sudo logs. One of our researchers actually, when she found out that we get the emails for sudo, actually kind of got very excited and said, your center, from the XKCD of kind of where did the sudo this message has been logged emails go, and in XKCD there's Santa keeping track of who's trying to sudo on systems that they don't. She was just really excited that I was Santa within our infrastructure and got to see the sudo alerts of people trying to do sudo on systems that they're not allowed to. Hopefully that answers the question.
Cool, thank you. Next question. Are you just using direct attached storage, or do you have a SAN? If you're using a SAN, how has your experience been with reliability?
Yes, we only use direct attached storage. We do not use SANs within our infrastructure. Probably the closest that we have is home directories are stored on a NetApp. So we've got NetApps for home directories, and that's about it. Yeah, generally SANs I have found to be overrated and kind of more complication than they're worth. But then the flip side is the primary system that we have for feeding the market data and the research data into our compute nodes is actually something we've ended up building in-house, where it's large clusters of local machines, basically using a key value store, just literally storing out, shooting out blocks of data across the network onto local applications that are then actually just consuming the data. And that has the indexes. So we got our own protocols and our own bits and pieces around there to actually keep the compute nodes saturated with data, because the complexity and the cost overhead of SANs just isn't worth it for us.
Any SAN vendors in the room? Good. Do you have an internal virtualization cloud? If so, what are you doing?
Yes, internal virtualization cloud. There was a stage about 5 years ago, maybe 4 years ago, where we did stand up OpenStack across some older machines for a while, and we tested it a little bit. There was an asynchronous routing bug that we had between the actual machines themselves coming out, and then the response packets coming back from the internet, where it was just causing some throughput issues for us. So as far as stability went, it ran for about 18 months with very, very little care and feeding. But eventually we scrapped it because we just needed to retire that hardware, and we couldn't be bothered about rebuilding it somewhere else. I'm very interested in some of the stuff SmartOS is doing with their containerization. I've been a big fan of Solaris zones and virtualization since I was an alpha tester on Solaris 10. But the only Docker instances we run in production on our team are a Team Fortress 2 server for Friday afternoon games.
That's what Docker was intended for, right?
Pretty much.
So you touched on this briefly, but what are your thoughts on the platform as a service options available in cloud providers versus the infrastructure as a service options to run your own setups in the cloud?
On what type of services?
Just like what's around, what do you think about PaaS, eh?
Oh, yeah. I think PaaS is good. I play around with it a little bit for some of my side projects. There's some bits and pieces like Glacier I'm looking into again, just because, especially when it comes to tape backups, we've had to pull a fair amount of data from tape recently, and we've had something in the order of a 5% tape failure rate, which is actually pretty good for tape, especially tapes older than 2 years. But it's too much of a failure for us. And so I like keeping an eye on what's out there. I like playing with what's out there. And there's some good stuff. The key thing is to ultimately focus on your workload. What does your workload profile look like? How sensitive is your data? Can your data be out there? Can it not be out there? We've got regulators that kind of cover what we can and can't do as well in some cases. But there's a lot of data. Like generally, market data is public data, really, after a certain age, at least from an exchange's point of view. And so there's lots of stuff that we'd like to have out there. It's just purely the costs are still not in the right ballpark yet where it makes sense for us.
Okay, we're out of time. It's lunchtime now. I don't know if Chris is doing a speaker clinic, but you can probably come and bug him.
Yeah, probably. Otherwise, I'll be over at the DOW stand as well.
Thanks very much. See you this afternoon.